much to the organisers. This has been great and really interesting, and it's really fun to have a conference on sort of the whole of someone's work rather than some little topic. I think it's actually really fruitful. I should apologise to all of you. This title bears relatively little resemblance to the title I gave. I mean, the talk bears a resemblance to the abstract only by virtue of the abstract having been so vague that I could have instantiated it in a number of different ways. That's partly because I didn't have, kind of up my sleeve, a set talk to give that seemed incredibly appropriate for a Howard Stein conference, and I thought that rather than just giving you something that wasn't quite relevant, I would use this opportunity to have a think both about some connections between the kinds of things that I've thought about in the past and Howard Stein's work, and also to kind of review what I think about a certain debate about Newtonian space-time structure that I wrote a paper on a few years back, and then lots of clever people pounced on and wrote lots of papers, and that I've never quite worked through my thoughts on. So that's what this talk is. So it's not quite a kind of, some of it's presentation of other people's ideas, some of it's presentation of my own, and it's not quite a kind of a paper as such, but hopefully it'll be somewhat interesting. Okay, so what I want to do is explore some Steinian themes. So I'll start with those Stein quotes, because that's how you do things at this conference, right? And then what I want to do is think about Newtonian space-time structure, which is something Stein's famous for, but actually argue that there's kind of two, I mean, someone else has argued this, David Wallace namely, but present this sense in which there are two kinds of space-time structure in Newtonian theories, and neither of them are the Steinian space-time structure. Right? And I want to sort of explore the ways in which these are actually compatible. I want you to think about space-time structure, to think about these two ways of thinking about space-time as being compatible, and say a little bit about how you might extend some of the morals you learn in this to the context of general relativity. So, section 1 will be where all the Stein quotes are. Section 2, I'll introduce these two different responses to an extra symmetry that sort of Stein's work and others doesn't really acknowledge in Newtonian mechanics, so I'm sure he's aware of it. One, a kind of space-time presented by Simon Saunders, Maxwellian space-time, and another Newton-Cartan theory, which I wrote a paper arguing that you should just think of Newtonian mechanics as Newton-Cartan theory, but obviously I'm not Newton or Cartan. This isn't mine. And then I'll look at how we could reconcile. This is something really odd that goes on here. Simon and I start from similar premises, give an argument, and reach divergent conclusions, which we tell our undergraduates shouldn't be possible, right? So there's something sort of strange going on here, and I think that both Jim Weatherall and David Wallace have shed some light on it, and I think some interesting things have come out of that debate. So some of the talk will just be kind of presenting those other people's results to you, but then I'll say a little bit about how I think about space-time geometry in light of what's happened in this debate. And then, as I say, I think you might not realize it by how much ink has been spilt on Newtonian space-time in recent years, but it's a bit niche. Right? Not everybody cares about the space-time structure of Newtonian theories. But I think that this particular debate actually has interesting consequences for how we think about debates in general relativity, which you might think are more relevant. I see lots of people in this room care about the structure of Newtonian theories, so it's not a niche in this context. All right, so I guess I knew in some corner of my head before I started thinking about this talk that the 1967 paper was both, I think, the first presentation of what we call Galilean or Neo-Newtonian space-time structure, right? And Stein's first paper. But I've only fully come to appreciate how mind-blowing that is, right? So a lot of my work is responding to what I take to be the kind of orthodoxy that everyone knows, right? And it's extraordinary to realize that someone's first paper could be the paper that established the orthodoxy that now everyone knows. But here's Stein telling us what we now all know, but we didn't back then, that in Newtonian mechanics, we should think of space-time as a four-dimensional real affine manifold, together with a one-dimensional real affine manifold time, an affine projection of the former manifold onto the latter, and on each fiber of this projection, a Euclidean metric compatible with the affine structure. So that defines what we normally think of as Newtonian space-time, right? We've got a spatial metric, a temporal metric, and a flat affine connection. And if those of you who teach philosophy of physics, when we teach undergraduates, you tell them about Newton's absolute space. You talk about the fact that Newton's theory obeys the Galilean principle of relativity, and you explain that Newton had surplus structure in his theory, and this is the sort of right space-time structure. So it's the received view in the sense that it's kind of one you might teach to an undergraduate. Right. Okay. So that paper began 50 years of talk about what the correct space-time structure of Newtonian theories was. Well, what's that debate really about? I mean, there's something sort of slightly funny about this sort of, people reformulate theories. There are lots of interesting questions about when theories are distinct, when they're the same. But generally people take themselves to be doing something about telling us something about space-time structure. But what is it? It's not a matter of determining the space-time structure of some alternative possible world, right? I think that some philosophers of physics sometimes think about some of our kind of counterfactual explorations as being about exploring the structures of other possible worlds. There are no Newtonian possible worlds. They have no matter. It wouldn't be very interesting to explore them. I doubt they have a space-time at all. And it's, of course, not a historical matter. There'll be very little of historical value in this talk. It's certainly not a matter of working out what Newton took the space-time structure of his theory to be. I take it that it's a question of identifying the structure in our theory that best instantiates our concept of space-time. And that's interesting because it teaches us something about the ways in which theories can be structured, and it's interesting because it helps us to persistify and explore a concept like space-time, which is pretty central to scientific practice. And particularly, there's going to be a light metaphysical touch on many things here, and obviously you can see that is relatively light touch, obviously. Some people think of this as finding the deep space-time structure of the world, but that can't be what it's about when we're doing Newtonian mechanics, at least. I think one of the reasons we might be curious about a question like this, even if you're pretty robustly empiricist, is that the notion of space-time is really central to determining the empirical content of your theory. In standard cases, understanding what space-time structure is allows you to predict the behavior of an important class of measuring instruments. That's one of the reasons why we care about finding space-time structure. You can kind of read off empirical content from space-time structure in a way that you can't from all of the messy dynamics. Okay. So, you've seen this quote quite a few times in the last few days. And it's really just up here to say that last aim, I take it, is something that Stein was extremely concerned with. There are lots of people more familiar with all of the aspects of his work than myself, but this question of identifying space-time structure and thus being able to read off some empirical content from a theory is one of the ways in which we get the laboratory inside the theory, right? Finding things that stand in for sort of measuring rods and clocks and measuring instruments in our theory is a useful thing to do. Okay, so I take it that early sign would be sympathetic to this kind of presentation of why we are interested in space-time structure. Here's another quote which very much falls into line. Lots of people have taken this to support their particular views, but it's something that falls into line with the way I think about space-time. So he's discussed this correct neo-Newtonian structure for space-time. He's done a lot of very interesting analysis of Newton. And then he sort of has this quote, which is sort of what's the upshot of all of this? And he says, look, if the distinction between inertial frames of reference and those which are not inertial is a distinction that has real application of the world, that is, if the structure I described yesterday is in some sense really exhibited by the world of events, and if this structure can legitimately be regarded as an explication of Newton's absolute space and time, it's certainly an explication of some sort, right? Perhaps it's not the same. Then the question of whether, in addition to characterizing the world in just the indicated sense, this structure of space-time also really exists, surely seems to be supererogatory. So one of the things I take this quote to reveal is, at the very least, that the thing that Stein isn't trying to do, right, is find the table-bangingly real container in which Newtonian mechanics lives. Certainly not a real container in some alternative possible world, which, in some presentations, you might think is what's up in these debates, and certainly not mine.
Is the emphasis on Steam's Howard's or
yes,
yours?
It's his, and this particular LaTeX thing bolds instead of emphasis. So yeah. So whenever you see a sort of scary blue word, it really ought to be in italics. I need to about that glitch. Okay, so that quote has been used to support ontic structural realism about space-time. And you kind of see why, right? sort of all that matters is the structure, you don't care about the stuff. But I mean, this is another paper. I don't really think there is anything like an intelligible position called object structural realism about space-time points. I'm not completely unsympathetic to other bits of structuralism. I think it gets particularly bad in the space-time literature. I mean, endless discussion of identity condition for points seems to be achieving exactly the opposite of the kind of spirit of the quote on the previous page. So I want to say that it endorses my particular view, which of course it doesn't really. It's a little bit of a stretch, but it does it better than the object structural realist. So I like to think we determine the space-time structure of a theory by applying space-time functionalism. So rather than structuralism, a kind of functionalism. Functionalisms and structuralisms have relationships, but at least I think this is a reasonably clear view. So space-time's a functional concept. So a field or object or whatever else in your theory is spatiotemporal by virtue of playing a certain kind of role in your theory. It's space-time by virtue of what it does, not what it is. And so what I'm trying to kind of capture here is I hope something of the instinct that, we go and we pick out a structure and we work at what it does in our theory, and then over and above what you've said there isn't enough further question to be asked about whether you've described the container, whether you've described the space-time. And so I'm not pretending that, Stein is really a closet space-time functionalist, just that he might be sympathetic to some of the spirit of this kind of project. Okay. In particular, and this brings me even closer to the previous quote, I favour what you might call inertial frame functionalism. So I think that in lots of theories that we're interested in, the space-time structure is the inertial structure. So the space-time role is satisfied by some object just in case it specifies a structure of inertial frames suitably defined. And I have a pretty thick notion of inertial frame in mind, so not just a frame in which a force-free body moves in a straight line, but one in which the non-gravitational interactions take a particular universal form. So if you think of how inertial frames function in general relativity, special relativity, or in, say, neo-Newtonian mechanics, I'll discuss other versions of formulations in Newtonian mechanics in a second. I'm thinking of inertial frame in that kind of full sense. So something that has a pretty robust connection to the rest of the dynamics. And this is sort of unargued for, and I'm happy to argue about it later, but I think it's somewhat obvious that if you have a structure that does this, it's going to connect space-time structure to the symmetries of the dynamics, and then it's going to thereby ensure a connection between space-time structure and what goes on in the lab, the bits of the lab we'd like to bring into our theory, those rods and clocks, if you like. And the rod and clock mention will, of course, I don't think I have an explicit reference to Harvey Brown here, but right, there are different bits of Harvey Brown's project, but one bit of Harvey Brown's project is to sort of argue that you get back everything you need operationally out of space-time by thinking about symmetries of dynamics and inertial structure. I'm very sympathetic to that. Okay, so good. Stein and I are in glorious agreement, except that, and I quake to do this, right? But I take it that there's been a bunch of work done on space-time in the last 50 years, and it seems enormously plausible to me that the orthodoxy is wrong. It's the problem with being smart enough to establish the orthodoxy, right? That then you're the thing that people react against. So I think a reasonable number of people would agree that the orthodoxy gives insufficient weight to one set of symmetries of Newtonian dynamics. So when you move to neo-Newtonian space-time, you worry a lot about Leibniz's kinematic shifts, the invariance of the dynamics under boosts. But we know, and we've known since Newton, that the dynamics isn't just invariant under boosts. It's invariant under arbitrary time-dependent translations, right? It's invariant under linear accelerations as well. And Newton knew that, right? He enshrined it in Corollary 6, the laws of motion. If bodies moved in any manner amongst themselves or urged in the direction of parallel lines by equal accelerative forces, they'll all continue to move among themselves in the same manner as if they'd not been urged by those forces. So we know in Newtonian mechanics that if you give equal linear accelerations to an entire system, nothing about the internal dynamics are going to tell you that you're accelerating. Linear accelerations are just as much symmetries of Newtonian gravitation as boosts are. So there is something very odd about the orthodoxy, right? It stops at an unstable point. Why would you worry about one set of symmetries in determining space-time structure and say Newton was wrong about absolute space and not take the next step? Okay, so that seems like a good question to ask. And it seems to me, pretty set that this orthodoxy is good for teaching students. It's really easy to understand Galilean space-time structure. It's a good stepping stone to understanding Minkowski space-time structure, but it just doesn't seem to be the right structure for Newtonian dynamics. But the trouble is, it's not totally obvious what happens when you take into account this accelerative symmetry. And in particular, Simon Saunders and I managed to write papers in pretty much the same year, starting from the same premises and reaching different conclusions, both coming to different conclusions about exactly what one should conclude about Newtonian space-time structure given that extra symmetry. We read each other's papers while we were writing our papers, and we talked to each other, and yet you won't find anywhere in our papers any explanation of where we disagree. It's a sort of, in retrospect, it's a very strange phenomenon. At the time, it's made perfect sense to me. I cite Simon's paper quite a bit. I borrowed quite a few things from his paper, but then came to a completely different conclusion. But yeah, and I'm going to say a little bit about how that might be possible in a minute. But so Simon argued for perhaps what, I mean, not necessarily if you read the literature, but what you might think is the obvious conclusion if you have this extra symmetry, this accelerative symmetry, right? He argued that we should move to Maxwellian, or what he calls Newton-Huygens space-time, because why not add a new name to the literature? I mean, you can argue Maxwellian could be misleading in various ways, right? But yes, terminology abounds in this particular domain. But so Simon argues that we should adopt a space-time that has much less structure than neo-Newtonian space-time. It has a rotation standard, but no structure that defines linear acceleration. So it has enough structure to account for the rotating bucket, the effects of the rotating bucket, but not enough structure to pick out indiscernible absolute accelerations. At the same time, I argue that when you take this symmetry into account, you end up at Newton-Cartan theory, geometrized Newtonian gravitation, a theory of curved space-time. So where you have a curved space-time connection that depends on the distribution of matter. So you still have, lots of the kind of structure that you do in Newtonian space-time. It's just a richer and dynamical structure. Okay. So how do we get there? Well, this is going to be very brief. I mean, feel free to ask some questions, but obviously I'm not going to sort of try and give all the papers in one. So this is not irrelevant. There's a very interesting role in all of this debate for exact formulations of theories. And by exact formulations, I mean what kind of mathematics you choose to represent your theory. So what Saunders wants to do is develop a version of Newtonian dynamics that's written entirely in terms of relative positions, velocities, and accelerations. So what he does is have equations of motion that are defined in terms of the relative accelerations of two particles, and you pick those out in terms of functions of just particle distances in a system. And so that dynamics is rather obviously and explicitly invariant under this larger class of transformations that leave relative positions untouched. So time translations, but also under rigid rotations, but also under arbitrary time-dependent translations. So under transformations that would correspond to giving a system an acceleration. And, I mean, he does lots more than this, actually. I mean, one thing I should say is that, I sort of make it sound like Simon and I had wrote the same kind of paper in the same year. I wrote a little paper saying that stuff I thought everybody knew, right? And Simon actually sat down and worked out a much more detailed version of how Newtonian mechanics looks in Maxwellian space-time than had been done previously. So, and he thinks through, I mean, he actually writes this in force formulation, and he thinks through the consequences for Newton's laws and how you rewrite them in this form. Actually, I highly recommend the paper. It's interesting. But the upshot of it all is that you have this theory, and the natural setting for that theory, and we'll say a bit more about what natural setting means in a minute. That theory is Maxwellian space-time. This space-time, it has kind of the sort of classic Newtonian structures, it has preferred foliation, it has Euclidean metric, temporal metric, and it has a standard of rotation, but no standard of linear acceleration. So it has no inertial frames, right? Because an inertial frame would give you a standard of acceleration. And what Simon has to say about inertia is really quite interesting. He's motivated to the view, in part, by thoughts about the empirical significance of global inertial frames in Newtonian dynamics. So there's a long-standing debate about how we think about cosmology in the Newtonian context, and worries about how we think about infinite homogeneous cosmologies. And there's a worry that something like inertial structure is just undefined in the case of a homogeneous infinite cosmology in ordinary neo-Newtonian theories. But Simon also points out that in island universes, I don't know if he's the first to point this out, I hadn't thought about it like this. He also points out that in an island universe, so a universe where all the matter is concentrated in one place, right, where you might think that some of the problems with cosmology and defining inertial frames shouldn't pop up. Typically, if you think about something like the solar system, unless you think the solar system is at the center of your island universe, you can expect the solar system to be experiencing a large gravitational acceleration, right? So there's every resource within Newtonian mechanics to become aware of the fact that you're very unlikely ever to access an inertial frame in the Galilean sense. And he sees corollary 6 as explaining why we can get away with treating the center of mass frame of the solar system as inertial. So it's precisely the fact that you might as well treat the center of mass frame of the solar system as inertial. It means you can apply all of Newtonian mechanics. But without corollary 6, you really have a problem, because you're never going to land up in one of these Newtonian inertial frames. Now, I sort of agree with all of this, but I reached a different conclusion of what the inertial frames are. I think you think the center of the mass frame of the solar system is inertial, right? But, or approximately inertial at least. But what Simon concludes is this just means that there aren't inertial frames in Newtonian mechanics. There are things we can operationalize and treat as inertial frames and therefore apply a certain formulation of the theory. But fundamentally, there are no inertial frames. And the Maxwellian theory doesn't just give you, it's not just that you reformulate Newtonian mechanics you give an alternative theory and that theory is more parsimonious or something. One of the thoughts behind Simon's work, and also mine, is that the Maxwellian theory reveals kind of something like the real space-time structure of Newtonian mechanics. Inertial structure is sort of surplus structure, and the implicit real space-time structure behind Newtonian mechanics all along was the Maxwellian space-time structure. This kind of point is a bit tricksy, where we wanted to draw the line between different formulations being different theories, etc. I mean, perhaps what I'm most attached to is whatever you think the move from Newtonian theories in absolute space to neo-Newtonian space-time, we're making that kind of move. Right? And one way of thinking that is not that I write a whole new theory when I write down neo-Newtonian mechanics. I'm allowed to refer to it that way, but rather I just give you a reformulation of the existing theory that reveals the commitments that were already there in the existing theory. There's a sense in which Newtonian mechanics was never really committed to absolute space. Okay, so that's Simon's view, in a very quick nutshell. Obviously the paper was an awful lot longer than that. The paper that I wrote at the same time really mostly just highlighted things that people in this room had said before and better. Although I'll say a bit about why I wrote the paper. But I just, the formal side of things is just to point out the following thing that's been well pointed out both by Michael Friedman and by David Malamud, for example, which is that if you start with a Newtonian structure, so you start with standard Newtonian structures, a temporal metric, a spatial metric, a flat connection, a matter of distribution, and a gravitational field, if you start with that structure, and then you notice this additional symmetry that I was just discussing, so the symmetry under arbitrary linear accelerations, and then you also notice that there's a freedom in the definition of the gravitational field, that the gravitational field is kind of gauge structure in a certain sense. And you notice that these two things have a kind of two sides of the same coin, so you notice that the equivalence of gravitational and inertial mass in Newtonian mechanics ensures that a gravitational field produces those universal accelerations. You then notice that any transformation of a certain kind of gravitational field is a symmetry of the theory as long as you also adapt your covariant derivative operator, your connection in the appropriate way. So, corresponding to the linear, so I mean this is just the equivalence principle in Newtonian form, right? Corresponding to the symmetry under linear accelerations is a symmetry of the gravitational field. As long as you do these two things in tandem, you'll always end up with a symmetry of Newtonian gravitation. And you can wonder, since you've got this symmetry and you've got these things that look like kind of gauge quantities and on exactly the same kind of reasoning, that you use to move from, say, Newtonian theories with a potential formulation in absolute space to, say, neo-Newtonians based on the field formulation, you can worry about finding invariance under these symmetries. And you might note that the thing that's sort of invariant is a kind of sum of the affine structure, the connection, and the gravitational field. And this was a slightly roundabout way of doing things, but if you looked at the properties of this sum, right, you might notice it had all the properties of a connection. This thing defines affine structure. It turns out to be a connection with space-time curvature. And it represents, in fact, the curved inertial structure of freely falling frames. It's just a connection of Newton-Cartan theory. I'm not going into the definition of Newton-Cartan theory here. I think it's hugely germane to anything we do. But there's this thought that, so part of the thought here, this is sort of in parallel with the kind of thing Simon was saying. One of the reasons for this presentation is just to point out that the structure of the curved inertial structure, the structure of a curved connection, is kind of there in neo-Newtonian formulations of the theory right from the get-go when you think hard about the symmetries. Okay, so in a sense all of that's really well known. I don't know if I'm in my silly eye, right? Nobody would present it like that. But the road from neo-Newtonian space-time to Newton-Cartan space-time is perfectly clearly mapped out in the literature. There's no claim to originality there. But funny enough, I wrote the paper, I thought everybody just thought this was obvious, but I wrote the paper because Simon Saunders told me to, which now then makes it really confusing that we then didn't explain why we disagreed. But I wrote the paper partly because Simon persuaded me that not everyone was aware of this, that the orthodoxy was pretty persistent, despite the instability of Newtonian space-time. And I wanted to kind of really highlight the degree to which it wasn't just that there was a Newton-Cartan formulation of the theory or a new Newton-Cartan theory that you should replace Newtonian mechanics with because it was better, but rather that just all the same moves that got you to Newtonian space-time pushed you to Newton-Cartan theory. So to even really sort of think about theorizing with Newtonian space-time was to just sort of sit in an unstable position. The argument had also often been framed in the context of cosmological puzzles, and I think the path to Newton-Cartan theory is perfectly clear, even where you have, say, an island universe that's sometimes thought to fix cosmological puzzles. So I also thought it was sort of, it's been discussed in a cosmological context, and it didn't need it for the argument. And I wanted to push this fact, which comes from my kind of inertial frame functionalism, right? That when you think about the inertial frames in Newtonian gravitation, you might well think, based on those kinds of empirical considerations that Simon referred to, that the real inertial structure of Newtonian gravitation is that described by Newton-Cartan theory all along. So by my lights, therefore, the real space-time structure of Newtonian gravitation is just the Newton-Cartan space-time structure. Okay, because the inertial structure of the theory is just the one described by Newton-Cartan theory. You're welcome to quiz me on all of this, whether you think it's a ridiculous thing to say. But I want to get on to the central tension. Because, as I said, you sort of we start from the same symmetry and we reach these radically different conclusions. And both of us think that our respective conclusions are not just competitor theories. So it's not just like Simon thinks a better theory than Newtonian mechanics is Newtonian mechanics in Maxwellian space-time, and I think a better theory than Newtonian mechanics is Newtonian mechanics set in Newton-Cartan space-time. It's that both of us think that somehow what we've done is reveal the implicit spatiotemporal structure in the Newtonian theory in the first place. And that looks like, peace is impossible between us, right? We can't both be right. So there's a question that Simon posed at the end of his paper, which is how do these two accounts of the space-time structure of Newtonian dynamics relate? And understandably, lots of people, often David Wallace, asked me this question over and over again after we wrote the paper. I've asked Simon the question too, and both stand there and I go, something to do with gravity. I'm just more worried about gravity than Simon is. And didn't really...
Is that verbatim?
I bet it was pretty much, much mumble gravity. Don't know why Simon's not worried about gravity. And Simon presumably said something much more verbose. But possibly not, and probably much more sophisticated if you understood it. But possibly not any more clear. So the answer to this answer, how do you answer this question is phone a friend. Is that? Yeah. Who wants to be a millionaire?
Yeah.
Yeah, okay, good. All right. Is that just Brits? I could.
No.
Is that
No,
Americans?
we have that.
Okay, good. So, enter. So while I thought, well, one day I should really get around to thinking really hard about what on earth Simon and I were saying, people were writing papers, helpfully. So one paper is from Jim, who pointed out that you can take a Maxwellian space-time, and how he defines a Maxwellian space-time. And this again, I want to highlight that the move suddenly to expressing Maxwellian space-time in generally covariant form sort of isn't completely benign here. I think it actually pushes which kinds of conclusions we reach about things. But he says, look, if you have a Maxwellian space-time where you try and define the rotation standard of Maxwellian space-time by thinking about an equivalence class of derivative operators, he shows that once you put the dynamics of Newtonian gravitation in Maxwellian space-time, the class of allowed trajectories given by some matter distribution uniquely determine a curved derivative operator, that of Newton-Cartan theory. So you take this structure and you put in gravitation, and then one covariant derivative operator gets uniquely picked out. So gravitation sort of turned out to be true. And Jim's really nice, right? So he concludes that I'm right. So here. So he took the arguments here to resolve the puzzle. Knox and orders do not end up in different places after all, except insofar as Knox takes gravitation influences into account all the way through her analysis. Once one fully considers the effect of gravitation in Maxwell-Huygens space-time, some more terminological proliferation going on, Newton-Cartan theory is precisely the result. So I mean, I take it that what that guy says is, look, you just put in gravity from the beginning, you get Newton-Cartan theory, and that's just the correct structure in this sense. It's just you've gone by this roundabout route where you start off with very minimal structure and then you add in stuff and you get more structure.
Good, let's stop right here.
But funnily enough, I'm actually not going to, in a sense, of course, I mean, this is really helpful and I obviously agree with Jim, but there's something prejudicial to Simon's case about sort of starting with trying to write down the theory in standard differential geometric terms, which is part of the problem with Maxwellian spacetime is it just doesn't sort of naturally lend itself to being formulated in the language of connections and covariant derivative operators, right? Because it doesn't have one. It has a standard of rotation. It's very easy to, especially if you write things down in coordinates and you think about coordinate-based symmetries, it's really easy to understand what it means to have a standard of rotation. But it's actually pretty hard to understand what it means to have a standard rotation when you think about derivative operators. I mean, perhaps not. Eric's sort of scowling, but I mean, I suppose I look at this and I'm like, but is there a derivative operator? There's an equivalence, but which one? Do I just pick one at random? But then I have to find more structure, so I don't know. So I think there's a little something in here that makes this feel like a sort of overly stripped down, sort of unworkable structure. And in particular, Jim, for example, doesn't put he doesn't do kind of sort of standard classical mechanical dynamics in the way that Simon does. So it's not quite clear how you put the dynamics into this formulation in particular. This sort of vector relationism that Simon's really interested in doesn't naturally translate into this kind of language easily. Of course, it can be translated because sort of, we have mathematical parallels between things, but it's not a natural language, and therefore it's sort of and it is the natural language of Newton-Cartan theory, and so therefore I think there's a sort of push to thinking that stopping at Newton-Huygens space-time is sort of not what one wants to do. So here's the second phone a friend option. David Wallace also wrote a paper helpfully saying what I should have said about the relationship between mine and Simon's work, but much, much better than I ever could. So what David does in that paper, in a small part of the paper, he basically does exactly the same thing Jim does, but he does it written in the vector relationist formalism. And I'm not going to go into the details of how this works, but I recommend the papers. But he spells out the fact that if you start with Maxwellian dynamics written in coordinate form and you think about the symmetries and then you add in gravitational dynamics, you can eventually sort of pick out, uniquely, you can pick out inertial structure that corresponds to the Newton-Cartan theory. But he doesn't conclude that this means that sort of the Newton-Cartan theory was sort of there all along in Maxwellian space-time, or sort of was underlying or something. I mean, it's perhaps there's less disagreement here than I'm making it out to be, but he makes it sound like I'm less correct than Jim does. So, and I'm going to advocate that less correctness because I think it's it. But I'm going to say that I'm going to contradict Jim for sticking up for me too much and say that David's right to be a little bit more irenic.
Look, I'm with you. I think you're completely wrong.
So what David points out is that there's, let me read the quote and then I'll say what we say. It says, Newtonian physics, regarded as the physics of the universe as a whole, or for an isolated subsystem as observed from within that subsystem, needs only Maxwellian space-time as background geometry. That term's important. In particular, it needs no affine structure, specified in advance to make sense of its dynamics. However, a Newtonian dynamical system does determine an inertial structure, which gets its operational significance from the behavior of isolated subsystems of that system, and its mathematical representation as a connection compatible with the Maxwellian background. If we adopt Knox's functionalist approach to space-time structure, the space-time geometry of Newtonian physics is just this connection. So there's kind of these two conceptions of geometry going on here. So once you recognize that kind of formally these two things are kind of compatible and when you define one, you define the other, there's still this sort of extra disagreement going on between me and Simon, which is that we're using different notions of space-time. And I mean, maybe I should just table thump and say mine's best, but I'm actually not sure that's true. I mean, and also I don't really care which one's true, but I do care about sort of careful conceptual housekeeping and keeping track of what we mean by our concepts in useful ways. So the thing that David's pointing out is that there are two kinds of space-time geometry applicable to Newtonian dynamics. And this is useful because these two kinds of geometry we usually think of as going together. We usually think of them as overlapping. In this case, they don't. So what he calls the background geometry is the minimal structure we need to presuppose to write down the theory. And the way he presents it is the kind of conception of space-time geometry that has its roots in Klein's Langen program. Space-time structure corresponds to the maximal symmetry group of the fundamental dynamics. Now, this is where I actually do start to think that how you write down the theory is rather important. And maybe this will become clearer when you think about general relativity. But, I mean, what you take the maximal symmetry group of the fundamental dynamics to be is going to depend to some extent on how you formulate fundamental dynamics. If you write down a coordinate form and point out that the symmetry group is the Maxwell group, right, then it's going to be rather clear that Simon's right about the background geometry. If you do write it down in differential geometric terms, you might wonder whether you should think of the maximal symmetry group as the diffeomorphism group. Right? You might kind of think trivially, all theories written generally covariant. They sort of, that if you think of the kind of the minimal structure you need to write down the theory, what's the sort of, anyway. So I'm a little bit, I'm somewhat concerned that all this ends up overly dependent on how you write things down. But maybe I'm wrong. Tell me if I'm wrong afterwards, Jim. Okay, so that's one conception of geometry. Another one is what David calls emergent geometry. And I am actually really interested in emergent geometry because I'm particularly interested in how we might recover geometry in cases where the fundamental geometry is very different from the one that we observe, for example. But that's not what we need to worry about here. So I'm kind of interested in cases like quantum gravity. But we don't need to worry about the emergent word here, although David sort of has some arguments about why you should think of this thing as kind of approximate and operationalized. But you can just think about the inertial geometry, and that's the kind of space-time that's picked up by the kind of inertial frame functionalism discussed earlier. And that kind of geometry reflects the structure of inertial frames, and it doesn't have to be thought of as emergent. Okay, so I think that distinction is actually really helpful. I think it's quite helpful to realize that there are these two senses in which we talk about space-time geometry in the foundations of physics. There are probably more, but there are at least two. And there are lots of questions you might have about those. So look, do those two conceptions of space-time structure have to be in tension? Or, so David's conclusion is sort of ironic. Simon and I are both right. Although really, it's very interesting that Simon seems to think that it says that he's right. So I may be misreading. Who knows? I never actually explicitly asked David. so maybe we just all see whatever we want to in papers. But I think David's saying we're both right. So he doesn't think those two conceptions of space-time structure need to be in tension, but he doesn't explore it a great deal. So that's kind of an interesting question. Another one is, look, and absolutely related. Can somebody like me, who just doesn't think that there's much to the space-time concept over and above stuff that's functionalistically acceptably definable, right? So things that you can talk about the kind of role something plays in your theory. You're not going to talk about kind of intrinsic categorical characterizations of space-time. You're not going to talk about continuousness or space-timiness somehow as part of your characterization. Can someone like me accept the background geometry conception? That's another question. And which conception is closest to the orthodox conception? How does this track, and or Stein's if those aren't the same, how does this track the kinds of ways people have thought about space-time in previous theories, or previous theorizing? Okay, so is there tension? Can these two conceptions of geometry coexist? Well, there's going to be a certain kind of person for whom they don't, or not in a kind of full sense. So there's a certain kind of person that's going to say, look, my concept of space-time has this, this containeriness, this space-timiness, and they're going to insist that that's a sort of essential feature of the space-time role, and that person's probably going to be tempted to think that the situation described here is one in which the real geometry is Maxwellian, and then you've got some kind of merely effective geometry. That incidentally ends up being the one that probably picks out lots of features of the room we're sitting in, but never mind that. So there's this kind of person who might think that they are in tension, or at least perhaps they're not in tension, but it's obvious that one is sort of superior, better, more metaphysically fundamental, something like that. Somebody who's inclined towards functionalism about this concept isn't going to accept that. The structure of inertial frames just is space-time. There aren't other questions to be asked about whether it's really space-time, right, on the kind of view that I have. So the functionalists should be able to accept this, but will also want the other definition. They'll want both conceptions to be functionally defined, right? So, and I don't think I think if you're a kind of functionalist about the fact that in certain scenarios, the fact that some particular functional role something's played kind of gets torn apart and there's two things, there's now kind of two conceptions of space-time, I don't think that's something I need to lose sleep over, right? Because I didn't think what was at issue here was describing the table-bound, fundamental, real, metaphysical container of the world. So I think the functionalists can accept the possibility of two coexisting functional definitions, especially when our theories have evolved in such a way that functional roles that once overlapped become distinct. Okay. And it looks to me like this conception of background geometry that David picks out can be given a functionalistically acceptable gloss. You just say, look, this is sort of not my project in a certain sense, or perhaps it should be, so I haven't got all the kinks worked out, but it seems perfectly plausible to me. You say something like, background space-time is whatever structure picks out the maximal symmetry class of the dynamics, and that looks like a kind of kosher functional definition. There are kinks to be worked out. Symmetry class of the dynamics is hopelessly ambiguous. We normally are talking about external symmetries and not internal symmetries. So I sort of wonder actually though if you have maximal symmetry class whether you'll capture the right kind of distinction, because if you have multiple interactions, their internal symmetry groups won't be the same, but they'll perhaps share an external symmetry group. The link back to empirical content is a bit less clear-cut in this background space-time geometry case. In the Newton case, the Maxwell geometry itself is going to tell you, it's got temporal and spatial metrics, so it's going to tell you some stuff about the behavior of measuring instruments. But it's not, for example, going to tell you which measuring instruments are subject to accelerations and forces, which the inertial structure automatically does. So it doesn't necessarily kind of tell you which measuring instruments you might want to trust. But it certainly has some empirical content. In other theories with more minimal background structure, direct links to empirical content may be minimal as well. So the more, so if you have this sort of background geometry and you strip too much away of the kind of inertial structure, then you might end up losing some of that kind of, that link to empirical stuff that you sort of might like in a space-time theory. But I think as long as you're aware that that happens, then that's fine. It's not, it's just one needs to be careful to track how these things work. Okay, which conception? I don't have time.
43 minutes.
It's okay. I might go to 50. Is that going to be a disaster? So which conception is closest to the orthodox? Well, who knows what the orthodox conception of space-time is, right? One view of the orthodox conception links it closely to kind of a sort of very metaphysically robust container view. And that person is going to think, as I said, that the background geometry is something like the real geometry. And that kind of view is just not, they're going to set my kind of maximal symmetry characterization. They'll add in some extra ingredients, or some extra implications for accepting geometry. But I don't like that kind of orthodox view, right? It's silly. So, but what about more sensible orthodox view? Here we go. Here's a sensible orthodox view. So this is a shortening of that original Stein quote, right? And another thing that Stein says earlier, which is just describing this project, is it says that the subject is Newton's doctrine of space and time, but I want to begin by outlining the language of present-day mathematics. Not what Newton says about this, but what is in actual fact presupposed by the science of dynamics that we associate with his name. So it looks as if Stein kind of pushes in both. This sort of looks like my inertial conception of geometry, and this looks like the kind of the minimal background that you need to presuppose to get on with doing the theory conception of geometry. And so maybe he's got both. And that's okay, because it wasn't necessarily obvious for a long time that these two things could come apart. So the quotes point in both directions. But one of the things that I'd like to think is that, given the kind of light metaphysical touch that's also contained within the kind of account that Stein has about what he thinks of the issue, that he might not be too bothered by discovering that there were two conceptions that have come apart. I mean, you're only going to be disturbed by that if you sort of have a kind of a metaphysical horse in the race of a variety that I'm not sure he does. So he might be perfectly happy to see two valid functionalist conceptions as space-time diverge. Who knows? All right. So that's all I have to say about Newtonian mechanics. But one thing that struck me that David doesn't develop at all in his paper, but I think is these two conceptions of geometry seem to me to kind of be applicable much more widely than just Newtonian theory. So in particular, what should we say the background geometry of general relativity is? Well, it looks like the background geometry is something like the manifold structure, right? Why is that? Well, there's a sense in which you might think that the maximal symmetry group of the dynamics is the diffeomorphism group. Or equivalently, kind of the minimal structure required to write down the dynamics is that of the manifold. On the other hand, it's the metric that specifies what I think of as the geometry, the inertial geometry in general relativity. It gives you a structure of inertial frames. So I think there's a lot more to be said here. But if you think of some of the kinds of debates that go on in general relativity literature, I mean, debates about whether the manifold or the metric represents space-time. Oh, look, you know, this sense of space-time, maybe you want to think of the manifold as space-time. This sense of space-time, you want to think of space-time as more richly structured. Don't lose any sleep. That's kind of a solution I like. There's also, people get into sort of, tie themselves in sort of surprising knots about what the real symmetry group of general relativity is, right? Or the real symmetries of general relativity, the automorphisms of the metric field in a particular solution, or is it the diffeomorphism group? At least it might make clear the sort of two senses, the sense in which both of these things are true. I also think it might give you one sense in which general relativity is substantively generally covariant. So its background geometry is bare manifold structure. By contrast to something like Newtonian dynamics, whose background structure looks like its Maximalian structure. So, I mean, the substantive general covariance debate, various people have precisified it in various ways, and there are some clear distinctions out there. But some of them don't seem to track anything we're very interested in. Right? So, for example, you know, there's a lot of talk about absolute objects in general relativity. But I mean, I don't know if I learned an enormous amount when I realized that, you know, the square root of the metric is an absolute object. Right? I mean, some of this doesn't seem to track the kind of thing we're interested in. But of course, in the questions of what's special about GR, there is something about the role of the diffeomorphism group in general relativity that seems different from other theories. And this might be a way of characterizing that. It's not something I've explored enormously, but I think that might be helpful for future debate. So I think that this twofold distinction that David Wallace gives is actually a very helpful one. And so that's why I should go with the person who agrees with me less. Good. So I mean, that's pretty much it. Just to repeat what I've said. Newtonian gravitation theory can rightly be said to possess two kinds of space-time geometry, depending on which conception we choose. That way of thinking about things tears apart two roles for space-time structure that we previously took to coincide, that I think do coincide in special relativity. For example, that's sort of our remaining example of one where these two things come together. The functionalist can be laid back about that. Nothing's at issue over and above the existence of structures filling certain functional roles. I might be okay with that. And those two kinds of geometry also come apart in general relativity. Thank you very much.